and also kind of remind you where we are and where we're headed. I'll say it again, we are working in the harder of the material for the semester, and we are right in the middle to the almost done side of chapter 11. 9 and 10, I think you remember, and I said it before spring break, and I'll say it here after spring break. Both of those are long chapters. Hopefully you're working hard in them, because now you have a test coming up, 12 days away, so that's still quite a bit of time. But I know these takes a lot of time for this material to sink in. So that's my way of encouraging you. Don't put this off. I know it's a busy time in your other classes as well, but as I said, literally after spring break, hopefully you got a lot of rest in there, because when we came back, there was just gonna go for 5 weeks, and there's no time for sleep. It's just go and get it done. That being said, like I said, that your test is coming up. It's Monday, not this Monday, but the following Monday, so it's 12 days away. And you really want to make sure you're working quite detailed in that 9 and 10, and hopefully moving on to 11. Those are the harder ones. Not to say 11 and 12 are easy, but I do think 11 is a little easier, and 12 is the easiest still of the 4, but still a hard one. And so you have more time for 9 and 10 to get into your system and digest it and understanding, as long as you are working on it now and not putting it off. So another just long way of saying the same thing I said Monday, and the same thing I said in lab on Monday is work on these. 12 days is not enough time if you haven't done anything in chapters 9 or 10. But hopefully you have. That being said, let's come back to this little chart. We have been making this long chart that is comparing translational motion to rotational motion. And so each of these problems that we do, we then have some kind of analogy. And we left off with saying that one important principle was linear momentum, or translational momentum, and the units are kilogram meters per second. So there is also this thing called angular momentum, which we defined here as a cross product. And so, as you might recall from the end on Monday, we spent the majority of time doing a cross product and what it is, and then we said, well, what is the angular momentum? We also mentioned the units, and we did that special case of an object going in a circle. I'll come back to it. But here's what we had on Monday. We had this ball on the end of a string, and we said, all right, if you take the ball and you move it in a circle, and I know this one goes a little fast, slow, but just pretending it goes the same speed. If I came over here and said, all right, here is the object on the end of a string. At that particular moment, it has some velocity, which means its linear momentum vector is mv. Its radial vector would be out here from the center. And if I go to calculate what is the angular momentum, this calculation would be divided into two pieces. The first piece, as I was trying to say, is what is the magnitude of it, and then the second one is what is its direction. So the magnitude would be r times p times the sine of the angle of what? And this is why we learned the cross product. When you write it as a cross product, it is the angle between r and p. So p is in the same direction as v, r is straight out. If it is as simple as moving in a circle, then it would be 90 degrees. And so we put a 90 degrees. And since the sine of 90 degrees is 1, I'll just replace it with a 1. And since the magnitude of linear momentum is mv, I'll put that in there. And so we have this equation often written in as mvr for the magnitude. But that is how we got the magnitude. Then we got the direction, and we said to make it a vector, we have to do a cross product. And so we took our right hand and we said, put your fingers in the direction of the first one listed in the cross product, which is R. So there is R. And then adjust your palm so that you can close your fingers towards the second vector, which is P. And so R cross P would be coming out of the board. And so the total description of that vector would be this. And that's where we left off. We said that's a good thing too, because what that says is not only do I have its magnitude, I have its direction. And notice its direction is in the positive k direction, or the z direction, which is what we said is the same direction you would say its angular speed is. And so angular speed and angular momentum are in the same direction, just like linear speed and linear momentum are in the same direction. Now, albeit a little bit harder because it is perpendicular to the plane of rotation, so you got to think in 3 dimensions. But other than that, there is a lot of analogies between the translational motion and the rotational motion. And so my translational motion and my rotational motion chart is now almost complete. Let me keep going here, because not often do we just think about a single object at some radius r. That's the easy case. That's the beginning case. What we often have then is something that we've been talking about starting in chapter 10, is let's just take a piece of plywood, cut it in some crazy shape with a jigsaw, put it up against the wall, drive a nail anywhere you want, and spin it around that nail. And so as this thing spins, then this piece here would make a circle. This piece here would make a circle. And that was our whole argument in chapter 10, that if you have a rigid object, and so something that cannot change its shape, all the pieces would make a circle when they go around. Even though the object is some weird shape, the pieces on the object make a circle. And so now you can see why I was going through and talking about the angular momentum of something moving in a circle. That was the easiest one to understand first. But if I were to ask then, what is the total angular momentum of this object? We're back to doing the same kind of pieces of information that we did back in chapter 10. We said, look, let's break this thing into a bunch of little pieces and add them together. And so if I call this little chunk right here the ith piece, then I am saying add up all the little pieces. And clearly some of those pieces are way out here, and some of the pieces are in close, like that one. And of course, the ones that are in close would have a different speed to them. And so a different linear momentum. They also have a different R. And because of that, they have a different angular momentum. And so each piece does not have the same angular momentum. But the whole object has a certain angular momentum. And so if I add them up, I would be saying add up these mass of the mth piece, the velocity of the ith piece, the velocity of the ith piece, and the radius of the ith piece. And fortunately, they all have angular momentum in the same direction. And so when we go to add up vectors, that is really nice when all the vectors are in the same direction. There's no components to have to worry about. So when I go to add this up, and before I add them, I will make a quick switch going back to chapter 10. How would I get the speed of the ith piece? I guess I would write that as the angular speed times the radius. And so now, maybe you can see where this is headed. But each piece has the same angular speed. It is in the same direction. And so really, this is the summation part of it, if you factor out all the other pieces. And we saw that already before. What is that? Right, that's the moment of inertia. And so this then is the symbol I. Put another way then, the angular momentum is the rotational inertia times the angular speed. And I'm going to put the vector over it here, since the magnitude of the angular speed together with the direction of the angular speed would be the angular speed vector. And so, although our definition of angular momentum was this, I had told you that that is a very useful definition for many reasons. And one of them we already saw. It gives the same direction of the angular speed as the angular momentum. But a second one is this one. And so if I come over here, then I can say that the angular momentum is the moment of inertia times the angular speed. And so this is really kind of one and the same. But I think you'll like this one and appreciate that one, because doesn't it look identical to the same equation we have for translational momentum? It is the inertia times the speed or velocity. And so it works out perfectly. And so there's our angular momentum. Let me take this one step further. Let me take the derivative with respect to time of this equation. And I should do the whole equation. So I'm doing both sides of the equation. Let me do the right-hand side first, because the right-hand side then would really be just a derivative of the angular speed, since the moment of inertia wouldn't change. Again, maybe I should emphasize, it wouldn't change for a rigid object. And that's all we're doing at this level. And so the moment of inertia is made up of the mass of the object and the distribution of that mass. And so if you add it up, you have a certain value. It's a constant. So I will pull that out in front and take the derivative. And I say that because what do I get here? Right, that's the angular acceleration. Isn't that Newton's second law? Isn't that then equal to the net torque? And of course, the other side of the equation here, there's not really anything I can do other than just to write it as the change of the angular momentum. But if I also write that one in my little chart here, here's what it's saying. It says that the torque, net torque, if there is a net torque, does what? Changes the angular momentum, right? So if I have no torque, what would that say about the angular momentum? Right, it wouldn't change. And didn't we do the same thing in chapter 9? Didn't we have over here an equation that said the net force on an object is equal to the change in momentum of that object? Now, granted, that was before spring break, but that was really our first step, our first section of chapter 9. Right? And so this we used very powerfully, because we said something like this. We said if the net force is equal to 0, then what? Well, then the linear momentum is equal to a constant. We called this conservation of linear momentum. And you might remember it was a very powerful tool. We had a lot of collisions, a lot of interactions with things going in straight lines and colliding and asking ourselves, did they stick together? If they did, we called it a perfect inelastic collision. We used conservation of momentum to find its speed. Fair enough? You might even remember, maybe I should have brought it out again. I had a track up here with two carts, and I had one cart that was stationary and one cart that was moving, and then they'd come along and they would hit. And what we said is, if you think of the two carts together as a system, then there is no external force. And because there is no external force, there would be no change in momentum, and we applied conservation of momentum. Now, we should be more specific. We really mean conservation of linear momentum. Because we can do problems just like that, but they have to do with rotation. Watch this one. This one, I can have a disk that is stationary and one that's moving. And so just like we did in Chapter 9, I can have one cart that is stationary and then one that is moving. And then they can hit and stick together. I could call that a perfectly inelastic collision. But what I knew in this one was that the linear momentum did not change. So what do you think is going to happen here when I have one object that is stationary and one object that is moving? Rotating is probably a better word. What happens if I put them together? I hope you see, just like the linear motion, didn't this one slow down? And so it lost some angular momentum. What did this one do? It's gained some angular momentum. What would I say about the total angular momentum? Right, and if I think of them as a system, then I can say the same thing. I can come over here and simply say, in very useful cases, if the torque and net torque is equal to 0, so if I think of those two together, then the angular momentum will not change. And so we have our third important conservation, and maybe I even should say last conservational principle. I should say last for mechanics and last for this semester. We'll get a lot more next semester. But this is our conservation of our angular momentum. And I don't know if you recall, but at the very beginning of this course, right on the first day or maybe the second day, I said we're really going to see 6 important principles. Newton's 3 laws of motion and the 3 conservational principles. We did conservation of energy in Chapter 8. We did conservation of linear momentum in Chapter 9. And now we finally hit conservation of angular momentum here in Chapter 11. And so all of our mechanical motion can be described from that. There is no other motion or property you need to know. So, do you want to know the answer to every mechanics problem in the entire? You get the idea. We've done many times. But it really is Newton's 3 laws of motion and the 3 conservational principles. And I don't care whether it's this class or any of your mechanics classes that you end up taking in the future, whether they be your, I'll call this your basic mechanics 1, and then you take our mechanics of engineering here, or when you transfer, you take an intermediate analytical mechanics or an advanced analytical mechanics or a graduate level analytical mechanics. If it's mechanics, Newton's 3 laws, 3 conservational principles, that's the answer to every single problem. Granted, it may be a lot of pieces going on and a lot of calculus and perhaps even a lot of multivariable calculus, which we don't do any multivariable calculus at this. But this is really the grand finale of this chapter. I told you it was a short chapter. It has a very important idea. It has, of course, this idea of angular momentum, which leads to conservation of angular momentum. In fact, it's probably worth at this point to show you some experiments involving conservation of angular momentum. The first one, I guess I really already showed you, is that if I take that stool and spin it, that has a certain amount of angular momentum. This, not rotating, has 0 angular momentum. If you add the two, that would be the starting one. And it would be fairly easy to calculate that angular momentum because I would just come over here and say, well, what is the moment of inertia of it? And as we got through here in chapter 10, or maybe as you're still learning along, that's the shape of the object. So that's a disk. And I learned that the moment of inertia for a disk is 1/2 mr squared. By the way, I have some good news for you. That table that is in chapter 10, I will photocopy it and it'll be the front page on your test. So you don't have to memorize all that table. However, that being said, I may ask you to prove that the moment of inertia of a disk is 1/2 mr squared, as we did in class. Okay? So you may not be out of calculating. I don't know if I'll ask that or not. Sometimes I do and sometimes I don't. But I will say this. These problems are hard and they are long. I will repeat, I will not give a problem that would be one that you need the moment of inertia to solve the problem, which then would also require you to calculate it. That's why I'm giving you the table. So a lot of the problems, you need the moment of inertia to do the problem. Maybe they involve conservation of energy, or maybe they involve conservation of momentum. Those problems is why I'm giving you the table. So if those problems involve things like rods and disks and spheres, you can just look at that table and get the moment of inertia for the sphere and do the problem involving, say, conservation of energy. And so your focus is not on coming up with what's the moment of inertia. Your focus is on using moment of inertia in a conservation of energy problem to solve it. You see what I'm saying? And so again, I will not give a problem that would be so long that half the problem would be calculating the moment of inertia. And then the other half is using that value with, say, conservation of energy and finishing up the problem. Now, don't get me wrong, I may give you 2 problems on the test, where one of them says calculate the moment of inertia, and the other one says use moment of inertia to then use conservation of energy to solve the problem. But those obviously are long problems. They involve 2 big pieces put together. And so that's, to me, that's far more than one problem is worth. And so your 5 problems will be in that category. All right, so again, plan on that table being there, so as you are working on the homework, you will know that, hey, if I'm doing a problem with conservation of energy or conservation of angular momentum, I don't have to remember that the disk is 1/2 mr squared. I can look at the table. All right, that being said, let me come back to this problem here. So here I have this spinning, and I can then look in the little table and say, this is 1/2 mr squared. And then if I gave the speed, the angular speed, then I could get the angular momentum plus 0. And of course, when I put them together, I now have what you might call one solid disk, although I didn't get it quite centered, but one solid disk. And if it was centered, it would have the same radius, it would have more mass. But you get the idea that then I would set that equal to the angular momentum and solve for, say, the new angular speed. And so I'm trying to hopefully get you to see as you begin to do these problems, and as we begin to do these problems in a few moments, the same way I would have done conservation of linear momentum back in chapter 9, I will use the same thought process to get problems involving rotation. Although I should probably point out that I think conservation of angular momentum is a bit harder. In fact, all of our rotational stuff is a bit harder. And a big reason why is right here, angular momentum, doesn't it depend on the rotational inertia and the speed? But rotational inertia or moment of inertia also depends on the distribution of the mass. When we did linear momentum, yeah, it depended on inertia and speed, but the inertia never changed. What would happen if I were to sit on a stool with some weights and my arms out, and then pull my arms in, or let my arms out, or pull my arms in, let my arms out. Now, clearly you can see my speed change. Why? Yeah, this is conservation of angular momentum, right? There's no outside influence on me. I'm spinning, and yeah, there's a little bit of friction, but this is a pretty good bearing system. And so I would say I have conservation of angular momentum, no outside torques. And so as I move the weights in and out, what I know is that number won't change. And I am changing that number, right? The moment of inertia is the distribution of the mass. And so as I bring my arms in, this number goes down, which means that number must go up in order for that to remain the same. It's really the same thing as this demo here. If I start with it and I just let it spin, but then I pull the string, and I won't pull it quite yet, as I pull it inward, now here I am on the outside, unlike this one I was on the inside. So here as I'm pulling on the string, it almost seems like, oh, maybe there is an outside torque. But wait a minute. As it goes around, which way is the string pulling? Is it pulling towards the center? So how much torque do I get? So here's the center. Here's the object going around. I'm going to pull it that way. Isn't that the radius there? What's the torque? Isn't it R cross F? So the magnitude of the torque is RF sine. And what would be the angle?
0.
Okay, zero. I'll call it 180 since R is out and F is in. But 0 or 180, what is sine of 0 or sine of 180? 0. So how much torque am I giving it? 0. And so this is a conservation of angular momentum problem. And you'll see it here. When I pull it in, doesn't it go faster? And so just like me sitting on the stool pulling my arms in, this number has to stay the same. This number is getting smaller, hence that number has to get bigger. Okay? And so we need to look at these and say, do I have a conservation of angular momentum? Here's a fun one. What if I were just to take a wheel that can rotate and then me that can rotate? And I guess right now I would say neither one of us are rotating. All right? So our angular momentum is 0. And it should stay at 0. So what do you think would happen if I hold it up above my head and I push it, I'll push it this way. So viewed from above, I guess it would be clockwise. What happens to me? I go counterclockwise, right? What happens when I stop it? And actually, maybe I'll use this one here. Grab both because this one's got that bent bearing. But if I go spin it, it goes one way, I go the other, my total is 0. If I stop it, then we should stop. If I spin it again, I should go one way. What happens if I turn it over? Then it goes the other way, so I should go back the other way, right? So that our total angular momentum is conserved. Conservation of angular momentum. So whatever I start with is what I end with. Of course, unless there's an outside torque, but I'm obviously trying to show you cases that don't have an outside torque. They are conservation of angular momentum. In fact, it can get multidimensional too, although now we're kind of crossing the line from what I said we would be doing. We'll just rotate around one axis. But let me do this. What if I started this? I'll just use this one here. But if I start this one and I spin it without sitting on the stool, you may argue, well, it's already spinning. Okay, fair enough. But isn't it spinning around what I would call an x-axis? I would say there's nothing around the y-axis. And so as this wheel is spinning, what would happen if I turned it this way versus this way, right? And so my angular momentum around a y-axis is 0 to start with. So it has to be 0 here. So it goes one way, I go the other. I turn it this way, it goes one way, I go the other. So that my total angular momentum around the y-axis is 0. Again, conservation of angular momentum. Both of these examples, the first one I did with the pulling the weights in, you might see this in sports. Gymnastics comes to mind. Ice skating comes to mind. I mean, what happens to the ice skater who's going around in this circle, and oftentimes at the end of the routine they kind of finish up at something like this. I think that's what they call it, a flying camel or something, and they got this leg out as far as they can with a heavy boot on it. And they got these arms stretched out here, and they're going around in a fairly slow rotation, and then what? Right, and then they pull everything in, and so they finish up the routine, something like this, as tight as they can get, and they're spinning around with an enormous speed. Conservation of an angular momentum. Tornadoes are the same type of problem. What happens as the air that's, way out here, a mile or two, going real slow, what happens as it moves and gets towards the center? It's going to have the same angular momentum. It's going to be going really, really fast. And so the airspeed out here is slow, but in here it's 200 miles an hour. And so we have I would say, the unfortunate benefit of conservation of angular momentum in that case. Gymnastics was the other one I was thinking of, right? I mean, if you watch some of these amazing floor routines, I mean, the gymnast will turn around, jump up, and then just midair pull everything real tight. What happens? They just spin around in this massive speed, and all of a sudden they do 3 flips and land on the ground. Like, whoa! How many? How quick was that? And so again, they are adjusting their moment of inertia of their body, which of course adjusts the speed so that you would have a constant. I mean, they can't do anything about it. Motorsports, motorcycles, fun one to watch. Because if you take a motorcycle and say you go off a ramp and the wheel's spinning like this, and you're in the middle of the air, and you apply the brakes, it doesn't do anything, right? You're in the air. What good is the brakes going to do? The wheels have some angular momentum. If you apply the brakes and they stop, where does that angular momentum go? To the whole body of the motorcycle. So the motorcycle goes up like this, and at some point puts on the brakes, and now the whole motorcycle does this. And the real impressive part is they get it all the way upside down, and then what? Yeah, then they give it some gas, and the angular momentum goes back to in this case, only the back tire, not the front tire. If they give it enough gas, they will stop rotating and they will just stay upside down. They give it more than that, what's going to happen? they're going to rotate the other way, and if done just right, then they nail their landing. So they go up, apply brakes, apply throttle, and land. And so a lot of maneuverability, even though you're not touching the ground. Same thing with the front wheel. You could come up here, and while you're in the air, you could take the handlebars and give it a crank 90 degrees. Well, obviously, this front wheel that was going around is now going around in a counterclockwise direction. Well, what else will happen then? Because when it went up, you didn't have anything rotating around a y-axis. And now you crank the wheel and it is rotating around a y-axis. So what happens? The back tire swings the motorcycle in kind of a flat, what's called a tabletop. And the wheel tire comes up this side and the back tire is going around that way. So the front tire is going around this way. The back tire comes up this way. And the motorcycle is kind of laying flat through the air until the driver turns the wheel back. And then the back wheel swings back. And the motorcycle, again, done right, nails the landing. I hate to say it, but even when done not right, it's still kind of fun to watch. Oh, hey, you missed that one, try it again. All right. But maybe that's just me. But there is the maneuverability using the conservation of angular momentum. You probably have done this without even thinking much about it. What if you're just riding a bicycle and you're going along and you get to your street and you want to turn right? What do? Don't you just turn the wheel? And then you turn the wheel the other way. And so if you turn the wheel to the left, you go to the left. Turn it to the right, you go to the right. Or maybe if I stand up, you can see it better, because here is the bike going down the street, and if I lean the bike then to the right, as viewed from above, isn't that a counterclockwise rotation? Now, there was no rotation before, so that means something must go clockwise, which happens to be you and the whole bike. And so you and the whole bike go around clockwise while your wheel is going around counterclockwise. And it's just the reverse this direction. This direction, the wheel would be going around from above clockwise, and I would be going around counterclockwise, so that my angular momentum remained zero, which was what it was before I leaned the bike, at least around a vertical axis. And so again, maybe a little too advanced, because I'm starting to get into multiple axes where the tires are rotating around an x-axis and then I lean it and now it's rotating around a y-axis. But I think it's important to see that how this conservation of angular momentum plays out. Another fun one to observe. Don't try it. If you want to watch it, YouTube it. There's plenty of them. What happens if you take a cat by its feet above the ground and let it go? Yeah, then cats are really good with angular momentum. They know that they can get their feet around pointing down. How? Okay, one option is definitely swinging the tail. So you have this cat, if you will. Let's say this is the head and this is the tail over there. If you let it go, as it begins to fall, it has no angular momentum. But if it starts to spin its tail, say clockwise, what happens to the rest of its body? It goes counterclockwise. And it goes around and around and around until its feet are down and then stops swinging its tail. So what happens to its body? It stops swinging. And so it uses that angular momentum and the advantage of its tail. Of course, I'm talking about a house cat, but if this was a big cat like a cheetah, and I pick on the cheetah, I don't know if you imagine a picture of a cheetah, but they run really fast, right? At what, 80 miles an hour or something? And their tail is a really, really long tail. Most tails on cats go about down to the ground. But the cheetah's tail goes down, and then so it doesn't drag, curls back up. And it's a really long tail. Why? So if the cheetah is chasing the antelope may be running 30, 35 miles an hour, which seems pretty fast to me, but it's nothing compared to this 80 miles an hour cheetah coming to it. The antelope's going, okay, I can't outrun this. If the antelope is somewhat smart, it'll say, but I got a trick up my sleeve. What am I going to do? I'm going to let the cheetah get close. But when it gets close, I'm going to make a quick turn. To the right, to the left, I'll just go to my right. So the antelope's running along, going to the right and saying, all right, I'm going to turn. Now, for the cheetah going 80 miles an hour, wouldn't it have to get a lot more force on the ground in order to make that same turn? And so I'm sure the antelope is saying they won't be able to do that. But the cheetah's got a little trick up his sleeve. What's the cheetah going to do? Spin its tail. And so as the cheetah gets close and sees the antelope goes that way and realizes, I cannot put enough force on this ground and push. All I'll do is kind of slide out if I push that hard. But I want to turn in this direction, so I'm going to spin my tail. And so it's got this really long tail, and it spins it and is able to make that turn and take advantage of the angular momentum that wouldn't otherwise exist. Right? And so it's that spinning that allows that sharp turn. Well, maybe I should show you one more, and then we should probably get into the examples here. Because all of these examples I've been showing you have been conservation of. Oh, actually, maybe I'll pause here, because I heard somebody say it. What about a cat without a tail? Will it land on its feet? And they will, but to understand it is a bit harder. So here's the front half of the cat. So here's the head of the cat. Here's the front legs sticking up. Here's the back. Here's the back half of the cat. Back legs sticking up. No tail on this cat. It can't just rotate its back legs because then its front legs would go this way. That's going to be a bit problem on the spine. Okay, so that doesn't work quite well. But obviously if something rotates one way, it has to go the other because the total angular momentum is 0 when I let it go. So while it's falling, the total still has to be 0, but somehow it's got to rotate. How in the world are we going to get both feet down, but both feet down so its spine doesn't get a full twist in it? And something us humans can't quite do. Our spine is not as flexible. But what if the cat rotated its lower body this way? What would happen to its upper body? Wouldn't it rotate that way? And so the cat would be, front legs up, head here, curved around near its butt end, right? But here's why I did that. What happens now if you rotate your back legs out? Your front legs go opposite. No twist of spine. Back legs out, front legs out. Rotate back body over, front body over, land on feet. And so with enough maneuverability in the back and enough instinctive knowledge, you could then twist around and get your backside or front side down, starting with your backside. All right, now back to what I was beginning to say here is I've been looking at examples of conservation of angular momentum, at least conceptually. We'll start to do some problems here so we can do them mathematically, and then we'll be done with the chapter. Then we'll go on to chapter 12, and then we'll have a test. All right. But I think this last one is kind of fun to see. Again, it's getting a little bit beyond the scope of this class, but like I said, it's worth seeing. And I think it's best, like all of these, to compare it to translational motion. So let me just talk about translational for a moment. Let me ask you this. What if I were to take something, say the Earth? Big round object, a lot of force of gravity. Let's say I were to hold something above the Earth. Now, if that object was at rest and I let it go, what would happen? It would fall straight down, right? I mean, the force of gravity is towards the Earth, right? There's the force of gravity. So in this case, you would say that the object starts to go faster. Fair enough? And you, of course, you would say it goes faster because isn't the force of gravity in the same direction it is moving? In fact, just to kind of remind you, what if I gave it an initial speed upward? What would happen to this? It would slow down. Force of gravity is still the same direction, right? But doesn't the initial speed have an impact on what happens next? So in other words, if I just drop it from rest, it goes down and goes faster. If I give it an upward speed, it goes up, but it slows down, at least until it stops, then it begins to come down, right? The one I really want to focus on is what if I gave it an initial speed sideways? What happens then? What did we say way back in chapter 6 when the force was perpendicular to the direction it's moving? What would that do? Right, it makes it turn. And so this object would just turn. There's a force on it, but it doesn't go faster. And so here's that analogy. I take the ball, if I just let it go, it goes faster and faster and faster. On the other hand, if the force from the string is perpendicular to the direction it's moving, what does the force from the string do? It doesn't make it go faster. What does it make it do? Rotate. It makes it turn, right? Change direction. All right. So if I came over here and I took this wheel and I start with it not rotating, and I let go with my right hand but hold with my left hand, probably doesn't surprise you that it falls. But what if it has an initial speed? And I let it go. It doesn't fall. It turns. Isn't that the same thing we're saying here? The initial speed is a crucial role here. And I agree, this one is probably not as easy to convince and see as the translation. So let's do some more talking on this. But I'm sure you're very familiar with the whole operation of a bike. If you want the bike to stay up, what do you need to do? You need to move, right? You need to have a rotational speed to those wheels. That's what will keep it stable. If you try to just put the bike up there and not move and balance it, good luck, right? But when it's moving, it's a piece of cake. It's the challenge I know I had with my 3 kids trying to get them to ride a bike. They would wobble, and I would tell them, it's easier if you go faster. And they would look at me like, you're crazy. I crashed once. I am not going faster and going to crash just to go faster. But it is more stable, and that's the whole idea of this angular momentum. So let me say it in terms of translational motion first, right? The force of gravity is the same, and it is down regardless of whether I release the ball from rest, whether I throw the ball up, or whether I throw the ball sideways. The force of gravity is in the same direction. But the result I get is dependent not only on that force of gravity, but the direction of the gravity in comparison to the direction the object is moving. And I think that's easy to overlook and quite surprising. We drew some pictures that look like this. We said if you had an object and it was moving that way, and you put a force that way, that would make it go faster. But if you put a force this way, that would make it go slower. If you put a force perpendicular to the direction it's going, it would turn. So it's not just that you have a force, it's also what force do you have compared to the direction it is moving. Let's do the same thing with torque. If I take this string that is then hooked to this axis, that is then hooked to this wheel, and I hold it right here, I would say that there is a distance r from that pivot point and a force of gravity mg. There is a torque. The torque is r cross F. And the magnitude of the torque would just simply be r and an m and a g, and I tried to set it up so that I'm at 90 degrees, and so sine of 90 degrees. That's the magnitude of the torque. But the direction of the torque is what? I'll put my fingers in the direction of R, adjust my palm so I can close it towards F, and I will get pointing out of the board. So the torque is in the Z direction. If I start with no motion, and I apply, in this case, a force, doesn't it go in that direction? So here, hopefully doesn't surprise you, that if I start with no rotation, and I let it go, that is saying there's a torque on the z-axis, and that should make it rotate around a z-axis. Isn't that what happened? I let it go, and it rotates along a z-axis. However, if I apply that torque, which is in a z direction, it won't change, but this we might think about as a change in the angular momentum. And so the torque for a small moment in time is the change in angular momentum. Or maybe to put another way, the final angular momentum is the angular momentum you start with plus the change. Okay, the change we just said is going to be in the z direction. I'm not going to change that. But did you notice what direction the angular momentum started with? If I hold it here and spin it, take my right hand, curl it in the direction of the mass, isn't my thumb pointing in the x-axis? So, like I said, this is getting a little bit beyond where we're going to stop here, but I'm saying the initial is in the x direction, and I add to it a small piece in the z direction. And so the vector goes from pointing that way to pointing that way. So it doesn't rotate around the z-axis. it precesses around the y-axis. And so again, just like this ball, when you give it a sideways speed, it gets pulled on. It doesn't go faster or slower, it just changes direction. Same thing with this spinning wheel. It does not spin any faster or any slower. It just changes the direction it is spinning. And so it just changes direction constantly. Sort of like a satellite going around the Earth keeps changing its direction, but it doesn't go faster and doesn't go slower. So, like I said, now we're starting to get into multi-axes of rotation, which I said is where we're going to stop. And so let me stop there and then call up your textbook here and work on some problems. Starting with a, I don't know if warning is the right word. Maybe I should call it a hint, because there is a couple of problems in this chapter that give students a hard time. They kind of come in two categories, and I want to give you a hint towards each of those. And before I even start doing some of the problems, let me give you a hint about things going in a straight line. Because with this whole chapter so far, I've been talking about things rotating on an axis. But what if I had something like this? What if I just had, and I'll use the baseball here again. And so the baseball's going here in a straight line. So the baseball has a mass m. It's moving at a speed v. And again, for simplicity here, let's say that there's no force of gravity. Okay, just kind of moving in a straight line. Does this object have any angular momentum? No, forget the ball spinning. Let's say the ball's not spinning. And I think most people's reaction here is no, it doesn't have any angular momentum. Not quite true. That's why I'm going to talk about this. Because it's not spinning and it's not moving in a circle, it's easy to go, oh, it doesn't have any angular momentum. But remember, what was our definition of angular momentum? R cross P. And so there's two things I want you to see in here. And first of one is, you might be surprised that an object going in a straight line does have some angular momentum. It's why we do the lab next Monday. It's a good one. And the third part of that is to look at the angular momentum of something going in a straight line. Because, like I said, it's just, I think, natural for people to say, no, it doesn't have any angular momentum. But as I will show you, that's just not true. And as you do the problems, you need to realize that. And as you do the lab, you will need to realize that as you do the lab. Notice then that the angular momentum depends on what you define as R. So you watch this for a moment. Let me come over here and say this object would continue along in this straight line if there's no force of gravity. Fair enough? But let me put my origin, say, here. I'll call that origin A. Let me put another origin there, origin B. Let me put another one here. I'll call it origin C. Let's do A first. When the ball is right here, and I go to calculate the angular momentum, and I'll just do magnitude first, what would R be? Well, I guess R would be from the place I'm going to calculate it to the ball. There's R. Fair enough? And so I'll put an R. The momentum is mv, and the angle would, I guess, be that angle in between. Now, I'll start off. Is that 0? No. So does this ball that's going in a straight line have any angular momentum? It does, doesn't it? And do you begin to see that the angular momentum would depend on where your origin is? Now, hopefully that's not a big surprise. Didn't we do that in Chapter 10 with both torque and moment of inertia? Didn't we say particularly the moment of inertia depended on what axis it is rotating about? So you can't just say, what's the rotational inertia of a disk? Now, you can say, what's the rotational inertia of a disk about its center? But when it gets off-center, didn't we have to do the parallel axis theorem? Wasn't that the point of the discussion? Wasn't that the whole point of deriving the parallel axis theorem? Wasn't that the point of part 3 of the lab this week? Was to remind you that the moment of inertia of a disk changes. It depends on where you are rotating it about. Torque, the same thing. Didn't torque depend on the lever arm? And so didn't the torque change depending on where you calculated it? So let's look at the angular momentum as measured from B. I guess from here to here would be R. And so I'll just do the magnitude. So there's R. It would be mv, and it would be sine of 0, or 180. I'll put 0. And what would that give you? So how much angular momentum do you have now? 0. And so I'm hoping you see two things here. One is the angular momentum is not necessarily 0 when it's going in a straight line. Could be 0, but perhaps it is not. So the angular momentum depends on what origin you're calculating it about, which, now that we think about it, wasn't the moment of inertia that way? Wasn't torque that way? So not a surprise, angular momentum is that way. And so all of these rotations depend on what are you calculating the rotational point about. And usually when something goes in a circle, it's easy just to do the center of the circle, and there wasn't really a discussion about what point. But when they start going in a straight line, now you don't really know what point to calculate. So just find one. And what I'm trying to show you here is two important things. It could be 0. It doesn't necessarily have to be 0. It depends on your origin. It depends on your calculation. So as calculated from point B, I say the angular momentum is 0. But as calculated from point A, it's not 0. In fact, let's look a little bit more at point A. Watch what happens when the ball gets a little closer. Say here. Wouldn't this be R? And so did R change? Yes. And wouldn't this be the angle? Didn't the angle change? So did the angular momentum change?
No.
You say no, why?
Because like the angle got bigger as the radius got smaller.
Yeah, okay, so radius got smaller, angle got bigger. Maybe those two balanced each other, right? Did they? Well, how about if I draw a triangle? This right here, let me call Y. Isn't R the hypotenuse? You multiply by sine of that angle, don't you get Y? So that R combined with that sine theta is going to give you Y. And I don't care where the ball is. It always gives you Y, doesn't it? And so that's what you're hopefully noticing here, that as this ball is moving, the angular momentum stays the same. And hopefully that's not a surprise. Didn't we just get done saying conservation of angular momentum? When should the angular momentum change? If what? if there's an outside torque. We're talking about something that has no forces on it. There are no torques anywhere in here. There is no way you can have a change of angular momentum. And so from that alone, you should have been saying, hey, this is conservation of angular momentum. It should not change. But hopefully you also see it in the mathematics and the geometry here that it would say the angular momentum does not change. So let me say it again. Hopefully you see all this. Number one, the angular momentum does not change, going backwards. Number two, the angular momentum is not necessarily zero. Could be zero. But the angular momentum depends on what point I am calculating it about. It's a constant, yes, but it also depends on what point. Oh, let's give it its direction here. What direction is the angular momentum? Let's make it a vector now. Now we know that it's y-mv. Doesn't it have a direction? All right, here's that right-hand rule again, right? So I would put my fingers in the direction of r. And I guess I would have to adjust my hand so I can close it towards P. And which way is my thumb? Out of the board. So isn't the angular momentum in the y direction? Or not y direction, the z direction? In fact, I bet it wouldn't surprise you that if I had a plastic arm sticking down with a little catch here, and that ball came along and landed in that catch, what do you think it would do? Wouldn't you expect it to rotate around point A? And so you would expect it to have some angular momentum. And would it be positive or negative? And it would be positive. So hopefully, and viewed in that sense, it doesn't surprise you that, number one, it does have angular momentum, and number two, it is in a positive z direction. On the other hand, if I were to have a little catch at point B, so I have this little plastic piece at point B, and the ball hits it, do you expect it to rotate? No. And so after the collision, it would have no angular momentum. So what must it have had to have before the collision? No angular momentum. I'll do you one better. What about this point C that we haven't calculated yet? What happens if there was an arm sticking up from point C with a little catch on it? What would you expect if that ball hit at point C? Would you expect it to spin around? Yeah. So I would expect this to have angular momentum. And would I expect it to have positive or negative angular momentum? Negative. And so I'll put that little catch up there because, again, I think it's easier to mentally see angular momentum when you actually see something going in a circle. But things that are going in a straight line do have angular momentum, and it's based upon where you calculated it. And so to finish this little helpful hint, because you have a couple of problems on the homework that if you don't realize things going in a straight line have angular momentum, you're lost. Okay? And so the examples I'm about to do start right there. They start with the idea of things going in a straight line. And they do have to calculate their angular momentum. And like I said, I think that's kind of hard to digest, and that's why we have part 3 on the lab Monday, so that you will go through and you will actually shoot your cannonball in a straight line, and you've got to figure out its angular momentum. In fact, the experiment we do next Monday looks a lot like this. You shoot the cannonball, and you have that same equipment we use this week where you have the track and you have a little catch out here. And you shoot the ball into here, and the whole thing begins to spin. And so hopefully giving you the visual effect that it has angular momentum. And then you using your knowledge of conservation of angular momentum to find out some information that they ask about in the lab. But finishing this up, if I were to calculate then the angular momentum as measured by point C, and I got so many colors up there, maybe I'll just switch over here to, well, I did red for the catch over here, so maybe I'll do red to mark from C. But at this instance, I would call that R, I would call that theta. And so the angular momentum would be this R, this M, this V, and the sine of the angle. But again, like we did for point A, if you look at that right there, call it Y prime to just to distinguish it from the other Y, then hopefully you will see that R and sine theta grouped together right here. So here's a triangle. Here's the hypotenuse R. R sine theta gives me Y prime. And so this is Y prime MV. Again, notice it is not 0. Notice it too is a different number than perhaps at A. And so how much angular momentum do you get depends on what point are you calculating the angular momentum from. Okay? And let's look at the direction now. What direction is the angular momentum? Well, if I do my right-hand rule, I will put my fingers in the direction of R. I'll need to kind of rotate my hand around so I can close it towards P. Which way is my thumb pointing? In. And so I get a negative K hat, as we kind of expected, that if it were to move along and go into this catch, it would rotate in a negative direction, what we would call a clockwise rotation. Okay? So, how much angular momentum it has when it moves in a straight line? Not necessarily 0. Depends on where you are going to calculate it. So, that being said, how about we try the first problem I have listed here, which is number 25, and you'll see that it starts off with an object going in a straight line. And let me just make it a little bigger here. And so number 25, let's read it together here. But it says no. This is not going in a straight line yet. That must be the next one. So, got ahead of myself a little bit. But nonetheless, you need this hint for the next one, and you need it for solving the problems. But this one, we don't have anything going in a straight line. That's, like I said, the next one coming up. But let's read this one here. This is just kind of your basic angular momentum. And it says the following. It says, a particle of mass 0.4 kilograms is attached to the 100 centimeter mark on a meter stick that is 0.1 kilograms away. Funny story. A couple years ago, I had a student who did really well on the third exam. It was a hard exam. It did really well. As they were turning in the exam, they said, I think I nailed it. I had only one little trouble on the last one, number 5. It said you had a meter stick, and if I just knew how long the meter stick was, I could have figured out the problem. So when the description meter stick is also a description of how long it is, and so note here that the meter stick is 1 meter. Okay, and if anybody asks you when the War of 1812 was, hopefully you will say 1812. All right, so here, when they say meter stick, I have then a rod that I know its length, 1 meter. And more than that, they say on here that we have stuck a little mouse. Maybe it's like a piece of clay. So I've got a meter stick with a piece of clay that I'm going to stick on one end of the meter stick. It's at the 100 centimeter mark. Okay? The meter stick then rotates on a horizontal frictionless table with an angular speed of 4 radians per second. Calculate the angular momentum of the system when the meter stick is pivoted around an axis A that is perpendicular to the table and through the 50 centimeter mark, and then B perpendicular to the table through the 0 centimeter mark. There's two parts to this. You'll see here in a second the angular momentum is different because the angular momentum depends on what axis it is rotating around. And so let's do A first. A is looking something like this. They have a meter stick, so here's the meter stick, and they have a wad of clay, 0.4 kilogram wad of clay at the 100 centimeter mark. So they're telling me it's at the end. Now they say it's rotating on a frictionless table. So let's pretend the whiteboard is the table and you are above the table looking down. So this is an aerial view looking down. And so the 50 centimeter mark is right here. And so they are saying take that meter stick and rotate it around its center. Now that's different than B. Over here in B, they are saying this chunk of clay is still at the 100 centimeter mark, but what is different is it is now rotating around an axis that is at its other end. And let's make sure we have the right axis. I mean, read it carefully here. It says the meter stick rotates on a horizontal frictionless table with an angular speed. And right here, when the meter stick is pivoted around an axis, and notice it says perpendicular to the table. So in my picture, perpendicular to the table is in and out of the board here. It's in the z-axis. Okay? And so they say this is a rotation of 4 radians per second. 4 radians per second. So same angular speed, but a different point. And then, of course, the idea of the problem is to show you that you will get a different angular momentum. Now, the things that are not listed up here, and the one that I was telling you a funny story about is, yes, we do know how long the rod is. The rod is or the length of this is a meter stick. I use the word rod because now I'm going to go and look at the moment of inertia and I'm going to treat this as a rod. And we did a rod. So more on that in just a second. But it's 1 meter long. And then they also give me the mass of the meter stick as a 1/10 of a kilogram. And so this is a 1/10 of a kilogram. But here's why I picked this one. Let's just calculate the magnitude of the angular momentum. I won't do direction. Well, maybe since I put direction up here, I will also do direction. Why not? But they didn't tell me whether it was rotating clockwise or counterclockwise. So that's kind of my choosing. In both cases, I have chosen to go in a positive rotation. So when it goes to calculate the direction of the angular momentum, both cases I'm going to say it's in a positive z direction. That is, it's rotating around a z-axis, and it's rotating in a counterclockwise direction. So I'll do a positive number. But I think the real point of this problem really is more like chapter 10, is how am I going to get then the moment of inertia? And so it's the two pieces added together. And the two pieces then are, number one, a meter stick, which I'm going to treat as a rod, and so a rod rotating around its center. You remember working that one out? Do you remember what we got? And I guess we don't have to commit it to memory. I did say that I'm going to give you that table on the front of the test number 3, but it was 1/12 ml squared, where m is the mass of the rod and L is the length of the rod. So there's the equation for the moment of inertia that we did in the last chapter. But I have to add to it this little blob. That's probably the easy one, because remember, the moment of inertia is to sum up all the masses and multiply by where that mass is squared. But I think they're trying to imply that this wad of clay is all half a meter away. So this would just be 0.4 at a distance of 0.5 squared. I'm pretty sure that's what they want to say about this blob of clay. They don't really give me any dimensions to this blob of clay. Would have been a little different had they told me the blob at the end was a disk, and they gave me the radius of that disk. Then I know they would want me to treat it as a disk rotating off center. This then is 4 radians per second and in the k-hat direction. Let me put in the rest of my numbers. The mass of the meter stick is 1/10, and the length of the meter stick is 1 meter. And then these numbers we already did. And so grabbing my calculator, I'll be able to answer what is the angular momentum. So 1/12 times 0.1 times 1 squared, I guess I didn't need that, added to 0.4 times 0.5 squared. Take that whole thing and multiply by 4, and I get 0.433. And again, since a lot of this is new to you, what would the units be? Well, hopefully, as we mentioned earlier, we didn't mention it today, but this should be a meter from the R, and then from here should be a kilogram and another meter per second from the linear momentum, right? And I know that's what we had on the board on Monday. But those should be the units for angular momentum. Is that what I got? Well, let's see. This would have been units of kilogram. That would have been units of meters squared. And then this would be radians per second. Let me just drop the word radians and put in per second. And sure enough, it does work out to what we expected. So our unit analysis stuff and our dimension analysis that we talked about in chapter 1 worked not only for our translational motion, but it works well for our rotational motion. As I come over here to part B, I would say the same thing, that I would take the inertia of the two objects, one being the meter stick and the other one being the blob at the end of the meter stick, and multiply by its angular speed. As we mentioned earlier, it should have a k-hat direction. Whoops, maybe I should complete part A by putting the k-hat in there. So I have not only a number and its units, but I have a direction. B, same idea, but things are measured from a different location. And so things like angular momentum come out a little different. Things like moment of inertia come out a little different. Torques come out a little different, although we don't have any torques in this one. Here I would have the moment of inertia of a rod, but it's off center. All right. So I remember how to get it on center. What if it is off center? What do I do? Well, that was, again, the whole point of our parallel axis theorem discussion, which was the whole point of part 3 of the lab on Monday, was to say, okay, I could get things off of center. So I'm going to apply the parallel axis theorem to get the moment of inertia of the rod, because the rod is rotating, but it's rotating off center. Of course, then I also have the blob. Now, the blob is, as we said over here, probably the easy one to do because it is just some mass at some distance. But that distance is definitely different this time. It's not a half a meter, it's a full meter away. And so the 0.4 is now 1 meter away. And so there would be my equation for the angular momentum. So putting in these numbers, I have 1/12. I have a 1 kilogram for the mass of the meter stick, and the length of the meter stick is 1. The parallel axis theorem then says that the moment of inertia about that point is how far did you move off of center. And in my case, it's a 1/2 meter off of center. So it would be a 0.1 times 0.5 squared. And then I have a 0.4 and a 1 squared, and then times a 4, and then a k hat. And so that's the difference between step A and step B, is really where it is rotating. And of course, you're going to get a different angular momentum. So 1/12 times 0.1 times 1 squared added to 0.1 times 0.5 squared added to 0.4 times 1 squared equals times 4 gives me a new and bigger value of 1.53 radians per second. Oops, sorry. I'm going to drop the radians. 1.4, and in terms of mass, I'll do kilograms. In terms of distance, I'll do meters. I'll drop the word radian and then just have seconds, and it's in a positive z direction, and there would be the angular momentum. So again, hopefully a straightforward one. It's a nice one in terms of angular momentum, but it's also one that shows you, see how the angular momentum depends on what point you're calculating it about, and in this case, which one it is rotating about. Let me use this as an opportunity to give you another hint, although the first hint I gave you on the homework I haven't even used yet, but that's coming up on this next problem. But you have a problem on the homework that has an object of mass big M and an object of mass little m. And it says find the place where the moment of inertia is the smallest. Now, the reason they say that is, as you can see here, doesn't the moment of inertia and also then the angular momentum, and then so also the kinetic energy, change depending on what point it's rotating about? So I would suggest that you use the idea of algebra and call that a distance x. If the whole thing is separated by a distance of L, then the moment of inertia would be mx squared for this guy, and this guy would be ml minus x squared. Fair enough? And so, of course, you can see then, doesn't the moment of inertia depend on what the value of x is? But the question is, find the value of x such that when this thing rotates, it will have the minimum or the smallest amount of rotational inertia. How are you going to solve that one? How do you minimize a function? And I hope it's sounding calculus to you, right? Take the derivative of whatever variable is changing, which in this case is x. So you are really saying, how does the inertia change with different values of x? You set it equal to 0, and that's where you find your minimums and your maximums, right? And of course, you have to verify it's a minimum as opposed to a maximum, and there's a couple of ways. Maybe taking the second derivative is the best way and see if it is concave up or concave down, okay? But that's what they're after with that one. And so that's my second hint for you as you get working on these homework problems, is that that's really a calculus problem. But it's got a beautiful answer, because when it's all said and done, it actually turns out that the x that you solve for, the x that has the minimum value, is also the center of mass of the object. So when an object spins, it's going to naturally want to spin with the lowest energy. So it spins around what point? Center of mass. And so unless you have some other reason, it will spin around its center of mass. If I pick this thing up and I spin it, it spins around its center of mass. Now that doesn't say it always has to do that. I could just as well put it up here, put a nail right there, and it will spin around that point. So I could force it to spin around another point. But on its own, it wants to spin around its center of mass. And that's the point of this problem. All right, well, I better move on so I can show you the first hint I gave you. I think it shows up in the number 37 here. 37, I think, has part of it moving in a straight line. Ah, yes, yes, there's the picture. So here it says a wooden block of mass capital M, so they got a little picture here, is resting on a frictionless horizontal surface and is attached to a rigid rod of length L and of negligible mass. Okay, so we don't have to worry about the mass of the rod. That'll change in the next problem. We'll build up, make them a little harder. It says the rod is pivoted at the other end. Now a bullet of mass little m is traveling parallel to the horizontal surface and perpendicular to the rod with a speed v when it hits the block and becomes embedded in it. So did you catch this bullet going in a straight line? Does it have any angular momentum? Now, of course, it depends what axis I pick, what origin I pick. But if I calculate it relative to that point, the answer is definitely yes. And that's what I want you to see, okay? Because A says, what is the angular momentum of the block bullet system? All right, now it says the two together. You know what it doesn't say is it doesn't say what before or after the bullet gets embedded. Well, before wouldn't make any sense because it's going in a straight line, and things go in a straight line don't have any angular momentum, right? No. Why did the author not even ask before versus after? Let's look at the forces. Let's look at the torques here. Let me draw a picture. If I take this aerial shot here, here's the block with the bullet approaching it, pivoting right there, distance L, capital M here, little v here. When this bullet hits the block, isn't there an interaction between these two? Doesn't the bullet slow down? Doesn't the block speed up? Okay. But if I put these two together as a system, the torque from one is equal to torque on the other. So isn't the net torque on the system 0? Although, let's be careful here. What's this doing? How about if this wasn't here? I mean, it probably has like a little bolt put here, but what if there's not a bolt? What would you have expected to happen if there was a bolt versus without a bolt? Yeah, if there's a bolt in here, well, don't you kind of expect this to go in a circle? And what if there wasn't a bolt? You would expect it to go in a straight line? And I guess what I'm really getting at here is this little bolt is supplying some interaction, right? It's supplying a force. Because without that bolt there, it would be a different interaction than with the bolt there. So with the bolt, it goes in a circle. Without the bolt, it doesn't go in a circle. So there is a force here. Now this is important because if I were to ask you, is the initial momentum equal to the final momentum? This will take us back to chapter 9. Do we have a conservation of linear momentum problem? When is linear momentum conserved? If the net force is equal to 0, then the momentum is constant, right? That's what that's saying. So you have conservation of angular momentum when you have what? No external forces. Do we have an external force in this problem? Yep. It's right here where the bolt is. Could I apply conservation of linear momentum to this problem? No. And I will tell you, I see this a lot on test number 3. All the time. I give a problem, it has external forces, and the students write conservation of linear momentum, and I just have to go, oh, bummer. Red, 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 red. It's all wrong from the very beginning. Missed the whole idea of conservation of linear momentum. Linear momentum is not conserved. You could not solve this problem correctly with conservation of linear momentum. However, there's more to this problem. You got a question?
So why can't we just include that point in the system, and then wouldn't it be conserved?
Well, okay, that point would be attached to the table. So, okay, so the table would have to move. So if I want to include the bullet with the block and the table. Now the table's probably rubbing on the floor. Okay, so I got to include the earth. Okay, so if I want to do the bullet, the block, the table, and the earth, I'm good. Oh wait, the earth is being pulled by the sun. Okay, so if you get where I'm going with this. Yes, I can have conservation of angular momentum if I keep adding objects, but at some point I might add so many objects that there's so many unknowns it doesn't help me. Yeah, so I can change, in theory, to a conservation, any problem to a conservation of linear momentum, but it still doesn't help me solve the problem because I've had to add so many things to it. And this is an example of that. All right, so let me say it again. I hope it's real clear. We talked about this in chapter 9, but it's worth repeating here. And as you get prepared for the exam, don't make that mistake on the exam. Step back, look at the problem, ask yourself, is it even doable with conservation of linear momentum? And if there's outside forces, the answer is no. And this is an example of that. However, come back to this little chart here. When is angular momentum conserved? We had it right here. Did we erase it? Yeah. Right. If there is no net torque, then the angular momentum is conserved. So let's come back here. We already know we have an outside force. But does that force result in a torque? How do you calculate torque? Right? Torque has 3 pieces to it. It has an R and an F and an angle. So how much torque do you get from this force? And I would say if you calculate the torque about this point, then wouldn't R be 0? The distance from this point to this point is 0. They're the same point. So the force is acting at this point. If you calculate the torque at that point, R is 0. So how much torque do you get? 0. So is this a conservation of angular momentum problem? It is if there's no torque. And there's no torque if you calculate everything from that point. That's going to be the trick. Because the whole reason the author did not ask you to calculate the angular momentum before or after is because the angular momentum of the bullet block system is conserved. And so it doesn't matter whether you do it before or after. And I would suggest before is a lot easier. Which then you also have to remember objects going in a straight line do have angular momentum. You've been waiting to ask a question.
Why is the force going in that direction?
Well, maybe I'll start. What if I did not have the bolt? Let's pretend there was not a bolt here, and this hit. What would you imagine this doing? Like that, right? So to keep this from moving that way, wouldn't I have to push it that way? So I would say the force is that way. However, you're right, as it begins to turn, say it's at this point. Well, I would say this is the direction while the impact is being made. But then once it starts spinning, the force is, holding it into place, so it's opposite of the direction of it. But during impact, the bullet's going that way, and this is going to take some momentum from it. And so the linear momentum after the collision is actually a little bit less because of that force. Yeah. Which is the whole reason why I would not want to solve it this way. Okay? I would want to solve it with angular momentum. This is the difficulty you're going to have on test 3. You got to look at the problem and say, how am I going to do this problem? Is this a conservation of energy problem? Is this a conservation of linear momentum problem? Is this a conservation of angular momentum problem? Is this a Newton's second law of motion problem? Now, it probably won't be Newton's second law of translational motion because that was chapter 5, and you can be well assured that's not what this test is about. But when it comes to the final exam, you don't know that. That's the tricky part. What principles are you going to use to solve the mechanics? Are you going to use principles of rotation or translations? Are you going to use momentum, energy, or Newton's laws? That's what the experience you gain by looking at these problems and knowing the good and the bad of solving this. Well, like I said, that was a long way of just getting to the point of I am then going to do the first calculation, which says what is the angular momentum, and I will go ahead and calculate the angular momentum before the impact, because the angular momentum before the impact and after the impact are exactly the same. So long as I measure things from this point, because it is only from this point where I can make the argument that the torque is 0. If I were to do another point like here, then the torque wouldn't be 0. And I could not use conservation of angular momentum. And I'd be kind of stuck there. But fortunately, using that point, I can use conservation. So I will say that I will do that and say, what is the angular momentum? And this brings me to the hint I gave you a little while ago, is here I have one object that is stationary and one object that is going in a straight line. And the one that is going in a straight line would look something along these lines, where before impact it'll be something like this. There's the R, there's the momentum, mv, and linear momentum, and there's the angle between them. And so this becomes an R, an mv, and a sine of the angle. And I'll take it one step further, like we did in my little hint. What would you say R times sine theta is? And looking at this triangle that has now been formed, if this is R, which is the hypotenuse of this triangle, and I multiply it by sine of that angle, don't I get L? And that is, of course, if we don't consider the block to have any dimension to it. And I think that's what they want in this problem, because they did not give me anything to work with in terms of the block itself. So they want me to say then that this is an MVL. Now, if I also make it a vector and do a direction with it, you can imagine when it makes impact, it goes and rotates it in a clockwise direction. And so this must be a negative k hat for the angular momentum. You can also get that, of course, from your cross product with your right hand. You can take your fingers and put them out in R, rotate it around, R cross P. My thumb is into the board, so negative direction, sure. So that is the angular momentum before and after the collision. I won't need to worry about whether they want it before or after. It's conserved if measured around this point. But look at B now. B says, what fraction of the original kinetic energy is converted into heat or internal energy in this collision? And again, we did problems like this in Chapter 9. Of course, in Chapter 9, we were talking about a linear collision, and we said, okay, the momentum before is equal to momentum after, and then we worried about energy and figured out how much heat is formed. Same thing here. Except instead of having conservation of linear momentum, we have conservation of angular momentum. But working out B, I would say the initial kinetic energy must equal to the final plus any heat that's created along. Now, they don't exactly ask for the amount of heat. They say what fraction of the original. And that itself might be a good question. They're asking for Q over initial kinetic energy. That's what they're asking about. And so that would come out to be, if I multiply everything by K initial, that would be 1, minus K final over K initial. And K final would be 1/2 I omega squared. Let me pause right there. Because after the collision, I would have this object going in a circle. So its kinetic energy would be thought of as a rotational kinetic energy. Before the impact, I would have translational. Now, if I look at what I did over here in A, then this angular momentum, which would be I omega, would be mvl. So omega over v would be ml over I. And so I'm going to take this information that we got in part A and put it over here for part B, so that this, and in fact, I'll just cancel off the 1/2. But I have the I over the M here. But the omega over the V squared is that thing. And so this is an M squared, an L squared, and an I squared. And a couple of things cancel. And so I now have an M, an L squared, and an I. I'll even keep going with that. In the numerator, I have M over L squared. And in the denominator, I have I. So let's talk about what would be the moment of inertia of this crazy thing. Now again, keep in mind that they're just saying this is a blob of mass. And so when the bullet gets embedded in it, I have a second blob of mass. They're each at a distance of L. So the moment of inertia should be little m L squared plus big M L squared. Just add the two together. So when I get a common, actually I'll cancel before I get a common denominator. There's an L squared in each term in the denominator that can be factored out. And then I'll have a common denominator of little m plus big M. And so that will become little m plus big M minus little m, which reduces to big M over little m plus big M. Yay! A lot of pieces to that. And of course, we've done the easy stuff because we just have haven't really given any size to our block. The next problem does give us size, but I know you will be so disappointed to hear this. There's a special meeting coming in here at 10 o'clock. And so they've kind of interrupted our class a little bit. So we're going to stop a little bit earlier here for today. Maybe that's just as well. You guys look like you've seen enough for one day. And let you work on it. But we come back Monday, let's add to this. And let's do a bunch more examples. And then we'll get into chapter 12 and finish up 12 next week. And then you'll be ready for the test on the following Monday. At least I'll keep my fingers crossed that you'll be ready for the test. 12 days. Work hard on these. There's a lot of little subtleties in here that